Okay, this is science paper 1. It's a continuation, isn't it? Yes, from 2020 question paper. So, then below is a diagram showing a stone. This stone here of mass 2 kg. So this stone has mass of what? 2 kg. That was pushed up a slope. This is the slope, isn't it? Up a slope from Q to what? To R. So it was pushed from Q to what? To R. Right together. And then they are saying 72 joules of work was done up a slope from Q to R. So this question is from work, energy, and what? Power. This question. So now, what you need to know is this. 72 joules of work was done up a slope from what? Q to R. Right? And we are told to find the potential energy of this stone at R after it was pushed from what? From Q to R. Using what? 72 joules of what? Of work. Right? What is the SI unit for energy? Joules, right? Now, the potential energy up a slope, the potential energy of an object on top of the up a slope is just equal to the work that has been done to push that stone up the what? Up the slope. Are you together? So meaning, what is the potential energy here? 72 what? Joules. So simple, right? Now, if the stone on B, if the stone falls through side RT, if the stone falls through side RT, which one is side RT? This side, right? Side RT, right? What would its potential energy be at S? S. And we are told that S, as we can see, S is the middle point of R and what? T. Right? From R to T, from R to T, here, what is the potential energy of this stone? 72, right? What would be the potential energy of this stone at half RT? What do you think we do there? We divide by 2, isn't it? So, B, we are going to have 72 divided by what? By 2, which will give us what? What are we getting? Is it 36?
Yes, 36.
36? Are you sure? 36 what? Joules. So this would be the potential energy at S. Is it okay? We cool? Okay. We move, isn't it? Number on C. They want us to calculate the height RT. This height RT. Right? And they also want us to calculate the velocity of the stone just before it strikes the what? The ground. So if this stone was to fall from this point up to the ground, we know that here, this is the ground, isn't it? Up to here. What would be its velocity before it reaches here at T? That's what they want us to find here. They also want us to find the height. Okay. So now we know that potential energy is equal to what? M what? G what? H. Mass times the acceleration due to gravity times what? Height. Okay. So now you look at the height here. The height is R what? RT. The height is from R to T that they want us to find. Meaning the potential energy that you are going to use is not going to be RS or TS. It's supposed to be what? From R to T. Right? And then the potential energy, we know that the potential energy from R to T, the potential energy from R to T is what? 72, isn't it? And then we are told that the mass of this stone is what? 2 what? 2 kgs. Right? And then the acceleration due to gravity is what? 10 Newton per what? Per kg. Acceleration due to gravity is 10 Newton per kg or 10 meters per second squared. It's just the same. Is it okay? It's just the same. So in this case, which one are we? Wait. Okay, let's just use the same one. 10 Newton per kg because we have also kgs here. That's why we prefer using this one. But I'm sure on that question we are given the one we are supposed to use. Are we given? Acceleration due to gravity?
But anyways, we know.
We can use this one, right? Yeah. So the potential energy here is what? 70 what? 2 equal to, what is the mass? 2 kgs. Should I indicate the, okay, it's okay. 2 by what? 10. By what? H. We're going to have 72 equal to, what do we have? When you multiply? 20 H. So to find H, we divide both sides by what? By 20. So H is equal to
3.6.
say what?
3.6.
3.6 centimeters or meters? Meters. So this is the height from R to T. So you can say therefore the height RT is equal to what? 3.6 meters. Is it okay? Questions? Okay.
Okay, just what?
Okay.
Where there is gravity, if I use 9.8 meter per second.
It's okay. Yes. That's why if you check in other books, there will be something like this instead of an equal sign. It means approximate. Yes. So we just use this one to avoid the decimal numbers. So it's just okay. Mostly in this syllabus, this exam that we are writing.
We use 10.
10. Yes. But when you go to that building there, you can use 9.8. No problem.
Which one? It
Yes. Okay. I hope we are cool on this one. Okay. Should I erase?
Yes.
Velocity. Look at this velocity. Are you given time? You're not given time. Right? The only thing that we know here, we know that we have acceleration due to gravity, isn't it? And we know that this stone is falling from what? This side. It is falling what? This side. They are saying that the velocity of the stone, just before it strikes the what? The ground, it is falling from this side. Because if I push this stone this side, is it falling?
No.
What is it?
It's going to be rolling.
It will be rolling, right? So meaning falling is this side, right? Okay. So now, in this case, what do we have? We don't have time, right? We don't have time. But we know that we have acceleration due to gravity, which is what? 10, right? We also know that this object is falling to which height? 3.6, isn't it? So we can use the formula of velocity to say the root of 2 multiplied by what? GH. Is it okay? Is it okay? So now from here, we have 2. What is the acceleration due to gravity is what? 10, isn't it? 10. And then what else? What else do we have? We have the height, which is what? 3.6. Is it okay? This and this, we are going to have 36. So we have 2 multiplied by what? 36. 10 multiplied by 3.6 is 36. If we multiply, we'll get what? 72, isn't it?
Yes.
Answer. What do you get when you punch on the calculator a lot of 72?
8.47. 49.
80.49 meters per second. So this is the velocity of the stone just before it strikes the what? The ground. Hope this question is okay.
Yes.
So like let's say we use like equations of motion, like one of the formulas for equations of motions. That will be also fine.
Yes, it's okay. It's okay. It is just okay. Okay, this one. Number 5. Number 5. Although this diagram, hopefully you can see, you can relate that this one is close, here is not close, here is not even that close again. So we have this where you have the spring is close together. Here the spring is stretched. Here the spring is what? Compressed. And also here it is stretched. Here it is what? Compressed. So when you have such a wave, this is a longitudinal wave. Okay? So now, before I even start answering, what you need to know is this. What you need to know is this. The distance, the close, these ones, where the spring is close together, it is known as the what? It is known as the compression. Here, at U, it is compression. Here also it is compression. Also at this point it is what? It is the compression. Now, the stretched part here is what is known as the what? The rarefactions. The rarefaction. Now, here, what is the distance? What will be the distance from this point to this point? This closer distance is the compression. So the distance from one compression to another compression, it is what is known as what? A wavelength on this type of what? Longitudinal wave. So we are saying that the wavelength represented by what? Lambda. For a longitudinal wave, we are saying is the distance between two compressions or two successive what? They are what? They are factions. Okay. So the distance from this compression to this compression, this distance is known as what? Lambda, which is the wavelength. And also the distance from this rarefaction to this rarefaction here is also what? The wavelength, lambda. When you are looking at what? A longitudinal wave. Are you together? So a very common type of a longitudinal wave is a sound wave. Sound wave is a longitudinal wave. What is a longitudinal wave? Now, what is a longitudinal wave? So a longitudinal wave, this is where the vibration of particles on this wave, because when we are talking of wave, we are talking of what? The disturbance that is causing what? The vibration of what? Of particles. Now, on the longitudinal waves, the vibration of particles is parallel to the what? To the movement, isn't it? To the movement or to the wave what? Direction. So look at this. This wave is moving this side, isn't it? So where do you think the vibration of particles will be? They will be going this side. Because they are parallel. And a very good example of this longitudinal wave is what? It's sound wave. Are we together? What else do we need to know here? Okay. The formulas, I'm sure you already know the formulas. Did I give you the formulas? Are you sure? Okay. So for the wavelength, for example, if I want to find the wavelength, I can use the if I want to find the wave speed, the wave speed is represented by the letter what? V. This wave speed, the units are in what? The units meter per what? Per second, or meter second inverse, like that. This one and this one is one and the same. This meter per second and this one is just the same, right? It's just the same. This one, for it to become like this, it means you have meter over second, isn't it? And this one has a power of 1, right? So we know that if we take this S on top, the power 1 will change the sign of it will be what? S inverse. That's what you have there. It's just the same. And then now the formula for finding this, you say V is equal to frequency multiplied by what? The wavelength. Right? Is it okay? And then, but we know that the frequency, if you want to find frequency, you can say frequency 1 over what? T. Isn't it? So meaning this is not the only formula you can use to find the velocity. You can also use this one. Since velocity is equal to frequency multiplied by what? By wavelength, isn't it? Velocity is equal to frequency multiplied by wavelength. That's what we have here, isn't it? And we know that frequency is 1 over t, right? So we can have V is equal to, where there is frequency here, we replace with what? 1 over t, multiplied by what? By wavelength. Meaning here we can have another formula, V equal to wavelength over what? T. When you multiply 1 times lambda, we are going to have lambda over what? T. So these are the two formulas that you can use to find the wave what? Speed. Is it okay? And then for the period D and the frequency, I already gave you the formulas, you know them. You have this one. You also have the number of oscillation per what? Per unit time. You also have, for the period, you have 1 over what? 1 over t. You also have the period to be equal to t over what? N. N in this case represents the number of vibrations, not the number of oscillations. The number of what? Vibrations. We are not talking of waves. Is it okay? So now here, I'm going to answer Jap to B. Okay. In what way is this wave the same as a sound wave? In what way is this wave the same as the sound wave? They are both longitudinal waves, isn't it? So you are saying A, number one, you are saying they are what? Both longitudinal waves. Simple. B. What are the regions U and W code? What are the regions U and W code? So according to what we have here, we said that the part which is close together, where the spleen is compressed, it is known as what? Compression, isn't it? So U is what? Compression, right? Compression. And then the other one, W. What is W? The layer fraction, isn't it? Layer fraction. Is it okay? And then C. C. Explain why sound waves travel faster in liquids than in gases. Now let me tell you something. Do you know that a wave is even faster in a solid than in a liquid? It's faster in solids. Sound waves are faster in solids than in liquid. A wave is faster in what? Solids than in liquids. Also again, this sound wave is faster in liquids than in gases. What do you think is the idea around this? In solid, it is faster than in liquid. And then in the gases, it is in liquids, it's faster than what? In gases. What do you think is the reason behind this? We are talking of what? Particles, right? The particles in liquids are closer than the one in what? In gases, right? So if there is a disturbance, we know that wave, this is the disturbance. Now this disturbance causes particles to what? To vibrate, right? If you look at the molecular arrangement in liquid, maybe we have something like this. These are particles, right? And then the molecular arrangement in gases, you have a particle here, a particle there, a particle there, a particle there. So, if you have a disturbance here, energy, it will be faster for energy to travel from this particle to this particle because they are close together. But in this one, for energy just to travel from this point to this point, there is time taken, isn't it? So meaning it won't be what? Faster than in what? In liquids. So here we are talking of what? Particles, right? So we are saying that here, particles in liquids So particles in liquids are close together than what? Than in gases. So this was the last question on number 5. Let's look at number 6. Let's look at it. Number 6. So waves, they don't miss. They don't miss in the exam. Waves, we are not only talking of waves, also water waves and the light waves. Okay, so we have another question here, question 6. A ray of light travels from air into water at an angle of 40 degrees between the normal and the incident ray. If this ray produces an angle of reflection of 29% or 29 degrees, calculate the refractive index of water, the critical angle of water. So here, we are talking of light waves, and this question is focused on refraction, not reflection, refraction, isn't it? Yes. So for reflection, what they mean is this. Let me show you what they mean. Air is a medium, isn't it? So a ray of light travels from air. So let's say this is the air, and then this side here, this is the boundary, and then you have what? Water. So this medium here from this point going downwards is what? Water. And then upwards there is what? Air. Right? Okay. So a ray of light is coming from where? From what? Right? So for reflection, a ray of light does not bounce back. Instead, it passes through the what? The medium. What is the medium we're talking about? It passes through what? Water. But for reflection, if it was reflection, it would have been what? Like this. It would have what? Bounced back like that. But for reflection, when a light wave is coming from another medium, it penetrates into another what? Medium. Now, what you need to know is this. This is what is known as what? The incident what? The incident ray. This line is what? The normal. Right? And then this one now, it will be the reflected what? The reflected ray. Right? Now, the angle of incident. The angle of incident known as I. It is from the normal to the what? To the incident ray. So from here to here, this is the angle I. Or if you want, you can say theta 1, no problem. So this is the angle I. Angle I, it means the angle of what? Incident. Angle of incident, which is what? I. And then this angle, look at this. This angle from the normal to the ray here, it is what? R. This one is the R. R is the angle of what? Angle of refraction. Presented by R. What else do you need to know about refraction? Here is what you need to know. Why is it that here, the angle of incident that we are given here is what? 40 degrees. And then after reaching in water, it became 20 what? 29 degrees. When you are coming from a less dense medium, you are going to a higher dense medium. The reflected ray comes closer to the what? To the normal. When it comes closer to the normal, it means the angle reduces, isn't it? That's why you have 29 degrees there. So if you are coming from a less dense medium, air is less dense than what? Water, isn't it? Yes. So that's why you have 29 degrees there. To calculate this, you need to know the formula of what? Snell's what? Law. You understand? Snell's law, we know that the N, which is the refractive what? Index, is equal to sine what? Sine I over sine what? Sine I. Sine theta in this case, sine theta is I. We are saying that I, you can say theta 1, or if you want, we can say what? Theta 2 as your refractive what? Index. So if you want, you can say N is equal to sine what? Theta 1 over sine what? Theta 2. Theta 1 is where you are coming from, and then theta 2 is where this ray has what? Has landed, which is what? In water, right? This is the formula you use to find the refractive what? Index. But we already know this, because always the refractive index of water, if you are coming from air, it will be 1.3 something, 1.33. Yes. So that's what you need to find there. We already know that the refractive index in air is what? 1. Are you getting it?
Yeah.
The refractive index of air is what? 1. So if you want, you can say N1 sine what? Sine theta what? 1 is equal to N2 sine theta what? 2. N1 is the refractive index of what? Of air. Right? And the theta 1 here is in air, isn't it? And also there is this one, N2. The N2 now is the refractive index in water. And the angle of what? Of the refracted angle, which is in water. Right? So which one should we use? This one, or this one is direct, right?
Yes.
So we have N is equal to sine theta 1, or I, is what? 40. Right? Divided by sine theta 2, which is what? 29. N is equal to, give me the answer. Sine 40 degrees divided by sine 29 is 1.33. 1.33. So this is it, the refractive index of water. Is it okay?
Yeah.
Simple, right? We are done with this one. We are done with this one. Now the next one is the critical what? Angle of water. Critical angle of what? Water. When do you have a critical angle? When do you have a critical angle? When you have a total deflection, isn't it? Yes. That's when you have a critical angle. So in this case, can I erase? In this case, to find the critical angle, you can say theta what? C. Theta C is given by the formula sine inverse 1 over n. What is n? N is the refractive index, isn't it? And in this case, the critical angle of what? Of water. Meaning the index that you are using is for what? For water here. Is it okay? So now in this case, now we are saying the critical angle is equal to sine inverse 1 over 1.33. What do you get as your answer? $49? Is it 49 or 48? 49. 49 what? Degrees.
Yeah, when you round it off.
When you round it off, it's 49?
Yeah, but it's 48.75.
48.75. Okay, you can round it off. So that's the angle of, that's the critical angle of what? 49 degrees. And this one, it's all, you've been finding this the whole semester.
This one she's doing nursing. She was already in 2.1. That's what they said. She did NS before.
Okay, so that's all about question number 6. That's all about question number 6.